Everybody, in this video I want to talk about a feature of the language of the Fortran language that is, while maybe not entirely unique, is pretty rare in terms of what other programming languages offer. And then we'll talk a little bit about how it works, and then I'll describe how it made implementation of a particular common algorithm a lot more straightforward, and how it can even have some performance implications for such an algorithm. So what exactly are we talking about? I'm talking about vector subscripts for accessing elements of an array. You're probably familiar with uh, accessing a single element of an array via a single subscript, or maybe even taking a slice of an array, taking elements 1 through 3 by using the slice notation. And pretty much all programming languages have that capability. But in Fortran, there's another way that you can access elements of an array, and that's by providing an array of indices, and it will access those elements of the array in that order. Let's take a look at some code and play with this a little bit to get a feel for what exactly does that mean and what does it look like. So we're gonna just kind of toy around with a little example program here. To start with, let's declare an array of integers. For example, let's use like the first 6 prime numbers. So like 2, 3, 5, 7, 11, and 13, right? We all know that you could, for example, print the third prime, right? Right. The third prime is 5, right? So that's accessing a single element of an array. You can, of course, just print the whole array, right? We get the whole array, 2, 3, 5, 7, 11, 13, right? We can also take a slice of the array. Let's take the first 3 primes, for example. Right? So we can print 2, 3, 5. Right? We can even take, for example, non-contiguous elements of an array with a slice notation by providing a third integer here that is the increment by which we're going to take specific elements, right? So we'll take elements 2, 4, and 6 in this case, right? Right, so we get 3, 7, 13, right? We can even go backwards. So if we take 6 and 2 stepping by -2, we can actually reverse the order, right? So now we can take 13, 7, 3, so we've reversed those. And all of that's that's all pretty convenient, but what if there's not some regular pattern by which we want to access elements of an array? For example, let's declare another array of integers that we may not even know how many of them there are at compile time. So let's just say that we'll just take 1, 2, and 3, right? I can now take the primes in my order and get 2, 3, 5. In fact, I can now even take elements multiple times. 2, 3, 3. And I can do this in any arbitrary order now, right? This is the specific elements I want from this array. Okay, that's pretty cool. But there's a little bit more to it than that. This appears to be, like constructing a new array, and then we're printing that, right? So I'm going to take those elements from this particular array and construct a new array, and then we'll print that, right? But it's actually slightly different than that. Let's take my numbers, and we'll make it 6 long, right? So the same length as the primes. So my order is going to have to be 6 long. But let's take these elements of that array. So now I can say my numbers in my order equal primes, and print my numbers. Now, this is actually, at this point, it's not quite standards conforming because I actually haven't assigned to all the elements in this array. But you'll see that I assigned 1 to 1, 2, then 2 again, right, which is why we get 5 now, then to 4, which is where we get 7, then to 5, so we get 11, and then back to 1, which is why we get a 13 there instead of 2. And then, of course, I haven't assigned to this element or the last element, so they have whatever. Right? And so this demonstrates that actually this is not constructing a new array. The vector subscript notation does not construct a new temporary array. It actually creates a mapping into the original array so that this assignment statement still functions correctly. It creates a mapping back into the original array, not a copy. And that's going to have implications when we talk about the algorithm that we're going to talk about here in just a second. So let's switch over and look at the code, and then I'll talk about the algorithm. Okay, so what's this algorithm I've been talking about? It's a sorting algorithm. Specifically, the algorithm is called quicksort. The idea is that we will decompose the array into smaller arrays recursively and sort the smaller arrays and then put them back together in the appropriate order. The idea being that we pick what's called a pivot element. We take all of the elements from the original array that are less than that element, sort them, then take all of the elements that were greater than that, sort them, and then put the array back together where the elements that were less than come first, then the pivot, and then the elements that were greater than. But in this case, we actually want to perform that sort without actually moving the elements around. In fact, we just want to know how would I reorder them such that they were sorted. That's the idea. So what's the order that they would be sorted? And so the idea here is that I'm going to create an array of indices. So if I use the vector subscript with the array that I just created and use that as the vector subscript, that will give me the elements of that array in a sorted order. So it will now be possible for me to provide a sorted array to other things without ever copying the elements. In fact, this is where the performance implications of this come in, and we'll see that here in a minute. So the idea is if the array has size 0, then the array of indices is size 0 as well. If the array is just a single element, well, the sorted order is just take that element. If there are 2 elements, then we need to determine whether to take the second one or the first one first. So if the first one is greater than, then take the second one first. Otherwise, take the first one first. And if there's more than 2, then we're going to go through this algorithm where we're going to say, choose a pivot element. Generally, somewhere in the middle of the array is fine. You can just choose the first element. You can choose the last element. The choice of pivot isn't all that important, but it's in many cases, you're going to be working with data that is already reasonably sorted. And so if choosing an element in the middle will result in kind of a balanced recursion here. Like we're going to get a similar amount of elements that are going to be less than as greater than, and so you'll have similar recursion on both sides of the algorithm. And that helps balance things a little bit. Um, but like I said, the choice of pivot isn't all that crucial. We're also going to need an array of the indices, right? So this is just an array from 1 to what was the size of the original array. Right? So this is just 1, 2, 3, 4, 5, up to how big is the array. And we'll see in a second why we're going to need that. The gist is I'm just going to need this original array. Like this is just going to be, if I use this as a vector subscript, I just get the original array back. Then we're going to use the pivot, and we're going to find out which elements in the original array are less than the pivot point that we chose. And this produces a logical, it's called a mask, but the corresponding true-false will correspond to whether or not that element in the array was less than the pivot point. Similarly for greater than. And then we can determine what were the indices of the elements in the original array that were less than the pivot by using the pack intrinsic with the indices array that we created, right? So now this is all of the elements in the array that are less than the pivot point, and what's their index. Similar for greater than, and then all of the remaining items in the array happen to have been equal to the pivot. And performing this step is actually important for if you would like what is called a stable sorting algorithm, meaning that if two elements are equal, they will not swap places. For numbers or simple data types, usually that doesn't matter. You wouldn't be able to tell. But when you start to get to sorting more complex objects, then it could matter. Like if I'm sorting by one thing, but they're different in some other way, I don't want them to swap places if they happen to have been considered equal. Anyway, so now we've got these arrays of indices of the elements that happen to be less than, greater than, or equal to our pivot. Then in order to get the sorted, then we want to get the sorted order of those elements. Right? So what we do is we use the vector subscript. So this is an array of indices. We're going to access those elements of the original array and ask what is the sorted order of those. Right? So this is that recursion aspect where we're going to do this recursively until we get down to smaller bits that we know we can either swap the order of or not and then put them back together. Similar for greater than. And then the sorted order of the whole array is the indices that were less than in the order if I took those elements and sorted them. Then the indices that were equal without swapping them around at all, and then the indices that were greater than in an order that if I sorted those elements would be a sorted order, right? So this will produce you an array of indices that if you use as the vector subscript for the original array will give you a new array in an order that is sorted. And then now we can talk about what are the performance implications of this, right? If you were to implement this in other languages, there's a couple of things that you're going to have to do. One is you're probably going to have explicit loops, right? You can't do this kind of vector subscripting into the arrays. You're going to have to loop through these items explicitly. You're going to have some explicit loops. There's no explicit looping here. So the vast majority of these operations can actually be done in parallel because there's not an explicit order that is required here. And second, you're probably going to actually have to either actually move the elements around or at least make copies of the elements to give to the next procedure. But we just said that this vector subscript doesn't actually make a copy of the elements. It just provides a mapping back into the original array, such that This is really the only place where real copies actually occur. We do actually have to take a copy of these indices to create the result array when we return from the function. Those are actually making copies. But we didn't actually have to make a copy of any of the elements in the original array in order to pass down the recursion. So the implications of that are that for intrinsic types like integers or real numbers or something like that, this probably isn't going to be of much cost because the cost of copying those intrinsic data types is relatively small. We're just copying little bits of data. But if we were going to use this algorithm to sort large complex objects where the cost of copying them would actually be very expensive, this allows no copies to actually happen. And because no copies actually happen, you don't bear the performance cost of making those copies. So we can figure out how to sort an array that would ordinarily be a very expensive operation because the sorting would involve copying these large costly objects. We can actually do that without doing any copies. In fact, by using this sorted order procedure, if you don't actually need to make a copy in the sorted order, if you just need to pass an array as an intent in argument to some other procedure, or even if it's not, doesn't have to be, intent in, it can be intent in or in out, because it's providing a mapping, not a copy. You can actually use the vector subscript to provide a mapping back into the array in the sorted order and still not actually make a copy of any of the elements, right? So the performance implications of this is that you could do very expensive sorting algorithms without making any copies. And so that's actually a very useful feature of the language, I think. So I hope you enjoyed this journey through vector subscripts in Fortran. Make sure you push that like and subscribe button because I'm going to keep making more of these kinds of videos for you guys, and I hope you find them useful. I hope you learned something.